In this video, we'll discuss quadratic functions. We're going to explore quadratic functions and also use quadratic functions to talk about those reflections and translations in our previous lessons. A quadratic function can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are constants and a is not equal to 0. If a equals 0, we're reduced to a linear function, so we need a to be something non-zero so that we get that x squared term to show up. The most basic quadratic function that we can have is x squared, and you see it graphed below. The graph of any quadratic function is called a parabola. All quadratic functions have this shape. What is the domain of x squared? Well, quadratic functions are a special form of polynomial functions, and polynomial functions have a domain of all real numbers. Looking at our graph, keep in mind that outside of this plane, the graph keeps going on forever and ever in the directions that it's already headed. So if we take the graph and we try to smash it like a panini press onto the x-axis, notice that we get the whole x-axis covered by that graph. And there we have the domain of x squared being all real numbers. Similarly, to talk about the range, we would trash compact the graph onto the y-axis. And in doing that, notice that from 0 up, going on up to infinity, the y-axis is covered. Our range starts at 0 and goes to positive infinity. Notice there's nothing down here in the negative y's. We have no negative y values at all graphed for this function, and that's how we have that range of 0 to infinity. On a quadratic function, we have a special point. It's called the vertex of the graph. It's where the curve turns. It goes a new direction. In this particular function, the vertex is the lowest point on the graph. It's also called the minimum point. And at the vertex, the y value is referred to as the minimum value of the function. When we talk about values of functions, we're always concerned with the outputs of the function. All other quadratic functions are obtained from this most basic one, x squared, by using transformations. Exactly what we talked about in a previous lesson. The b and c in that standard form, f of x equals ax squared plus bx plus c. The b and c affect the location and are related to horizontal and vertical translations of the graph. The a affects the width and the orientation of the graph. And by orientation, we mean whether it's just like our x squared going up, or it's been reflected across the x-axis and it's going down. So A includes that reflection across the x-axis that we've seen before. We can also rewrite the quadratic function into a new form. F of x equals a times x minus h squared plus k, which actually tells us exactly how the graph was shifted. And this is called the vertex form, and we'll practice it in a moment. But I do want to point out that we used h when we talked about translations for the horizontal translation, and we used k to represent the vertical translation amounts. That was intentional, that we chose h and k for our translations so that we could be reminded of them here in the quadratic function vertex form. And there's one more thing that I forgot to write in here. There's something called the axis of symmetry. The axis of symmetry is a vertical line passing through the vertex. And the idea with the axis of symmetry is it cuts the graph in half so that the graph looks the same on both sides. The axis of symmetry is almost, you could almost say it's a mirror reflecting the graph across itself. And so on this very basic x squared graph, our axis of symmetry going right through the vertex is the line x equals 0. Notice the vertex values, the vertex coordinates are 0, 0. The axis of symmetry x equals 0 will always match the x coordinate of your vertex because it has to pass through the vertex. This axis of symmetry is an imaginary line It's not a real line, it's not part of the graph, but it is an important feature in talking about parabolas. In the problems given here, let's see if we can determine the vertex and the axis of symmetry. And so we have this lovely blue graph. I will use orange to call it out. Here's my vertex here right in the middle where the graph makes the turn. And yes, it is labeled 0, 2. My axis of symmetry is given by this pink vertical line. Looking at it, my equation of the axis of symmetry, x equals the x-coordinate of the vertex 0. In the second graph, my vertex here, there it is, 2, -1. Axis of symmetry here in pink, going through that vertex value. X equals 2 because 2 is my x-coordinate of the vertex. Let's look at some blank ones now. I'll do number 1 and I'll leave number 2 for you to try on your own. Use the graph of the quadratic function to identify the vertex, the axis of symmetry, and whether the parabola opens upward or downward. And so the idea of opening upward, that's like a cup. Opening downward would be like an umbrella. Cup or a bowl. You could say a bowl. Right, upward is like a bowl, downward's like an umbrella. And so we look at our first problem. This is definitely opening up. To find our vertex, we start on the graph. We just kind of follow it down until it starts to turn. Right when it makes that turn, that's going to be our vertex. And our vertex coordinates, -2, -1. So -2, -1 on the graph. And then if we want to find our axis of symmetry, we draw a vertical line right through that vertex. And our axis of symmetry equation is x equals -2. Again, referring back to our x-coordinate of the vertex. Axis of symmetry will always be x equals the x-coordinate of your vertex. Try number 2 on your own. See if you can get the same answers that I got. Take a look at the OneNote when you get a chance.